and subjective. I mean, the polarization is not defined before the act of observation, and it's only the act of observation through which the polarization is defined. So that means the reality is not objective, it's subjective. Okay? So indeterministic, intrinsically indeterministic, subjective, whereas the other state is intrinsically deterministic and objective. You may disagree with it, and that was the reason that when the quantum mechanics was invented in the beginning of the 20th century, there were actually two interpretations. One was called hidden variable interpretation, and the other is called Copenhagen interpretation of quantum mechanics. So we understand, well, we try to, in the history, we try to understand these states in two different ways. The first is the hidden variable interpretation. The hidden variable interpretation assumes that this state is just like a classical probabilistic state. Okay? And this indeterministic behavior is there because there are certain variables which are affecting which determine the outcome of an observation, and since these variables are not known, and that is the reason this state is indeterministic, just like the coin. But in the case of coin, we know that which are the variables which determine the outcome of your experiment. But in this case, in the hidden variable interpretation, we are supposing that there are certain variables which determine the outcome of your observation, but these variables are hidden. We don't know. Our experiments are not able to measure these variables. So this superposition state of the photon is like a classical probabilistic state in which polarization of the photon is defined before the act of observation through a set of unknown variables, so-called the hidden variables. So if that is the case, if there exist certain variables and these variables are unknown, so that means that the quantum mechanical description of reality is incomplete, because we are not incorporating these hidden variables in the description of reality in the quantum mechanics. So that's the outcome of this supposition. The state vector provides incomplete description of reality, just like this state, which is incomplete description of the state of the quantum. Only because in this case, the only difference is that in this case, the variables which determine your outcome, they are not hidden. We are just ignoring them deliberately. And the other interpretation, that is called the Copenhagen interpretation. By the way, this interpretation was pioneered by Einstein. So according to this interpretation, the world is deterministic and objective. So if the world is deterministic and objective, then it means that the quantum mechanics is incomplete. The other interpretation is the Copenhagen interpretation of the quantum mechanics, which was pioneered by Bohr. It says that there exist no hidden variables. The state vector provides the most complete description of reality which could possibly be provided. So if that is so, then it means the world is inherently deterministic and subjective. Okay? And obviously, in the early history, we cannot decide it through experiment that which interpretation is correct or which is not correct. And then in 1935, Einstein came up with the thought experiment, and from this thought experiment he tried to argue that the Copenhagen interpretation of quantum mechanics is incorrect. There must exist the hidden variables, so that means quantum mechanics is incomplete, nature is deterministic and subjective. So what was the EPR argument? The title of this paper was, "Can quantum mechanical description of physical reality be considered complete?" The paper was written by Einstein and two of his young colleagues, Podolsky and Nathan Rosen. So what was the EPR argument? But before I discuss the EPR argument, since this argument make use of certain particular type of quantum mechanical states, which we are called the entangled states, so let's quickly review what are the entangled states, and then I will discuss the EPR argument, which is based on the entangled states. we have already seen that an arbitrary state vector in two-qubit system will be this one. In this case, you know that's a four-dimensional Hilbert space. You have four basis vector. So an arbitrary state will be just a superposition of these four basis vector. So let's consider some states in this two-qubit system. Suppose the state is this one. So that means that I'm supposing that this coefficient is 1 over 2 square root. This coefficient is also 1 over 2 square root, and the other two coefficients are 0. So that is a specific state. So you see that in this case, this state can be decomposed into the two states, the state of B and the state of A. You just have to separate this 0 from this one. We know the second 0 that corresponds to the B, and the first corresponds to the A. So this state can be written as a product or direct product of a state of B and a state of A. So such kind of state is a kind of state which can be factorized into a possible state of B and the possible state of A. These are the possible state, one of the possible state of A and B. But not every state can be factorized in this way. So suppose this is another state in the same two-qubit system, in which this coefficient is 1 over 2 square root, this coefficient is also 1 over 2 square root, but these two coefficients are 0. Now here you can see that you cannot factorize, you cannot write this state as the product of a possible state of system A or system B. And similarly, if you think of this state in two-qubit system in which this coefficient is 1 and this is 1 over 2 square root, 1 over 2 square root, but these two coefficients are 0, so that the resultant state is this one. This can also, you cannot factorize it. Such kind of states in two-qubit system which cannot be written as a product of the possible states of the system A and B, we generally call them entangled states. Okay? So this is an entangled state, this is an entangled state, but this is not an entangled state. Why we call it entangled states, that will be clear enough. We actually call them an entangled state because in this case there will be certain correlations between the state of the system A and system B. What will be that correlation? Suppose that you measure this state and you measure that the state of the system A. Now, according to this, if you measure the state of the system A, there is a 50% probability that it will be 0 state, and there is a 50% probability that it will be a 1 state, because both appear in the state vector, and the coefficient is 1 over 2 square root. But at the same time, it also tells me that if you find that the system A is in the state 0, then the state vector will collapse into this one, and that necessarily implies that the state B will be in the 0 as well. And if you measure that the system A is in the state 1, then since there is only one component in which the A is in state 1, so the state vector will collapse into this vector, and that necessarily implies the B will also be in state 1. Okay? So if A is 0, if the result of if the state of the A is 0, the state of B is also 0. If the state of A is 1, the state of B is also 1. Whereas in this case, if the state of A is 1, then the state of B must be 0. And if the state of A is 0, then the state of B must be 0. So in this case, the observations on the system A and B, outcome of the observation on the system A and B are correlated. So that's why we call them the entangled state. So how we can have these kind of states? You can have in many different ways. For example, think of pi naught. It's a meson, and sometimes it is disintegrating to the two photons, and we can calculate by applying the law of conservation of angular momentum that the state of these two photons will be this one. So it will be an entangled state. So that means if the first photon is horizontally polarized, then the second must also be horizontally polarized. And if it is vertically polarized, then the second will also be vertically polarized. But most of the time when we do experiments with the entangled photon, we do not produce them in this way. But actually there are experiments in which we have studied the entangled photon produced in this way. We produce the entangled photon through the atomic cascades in which the electron go from one state to the other state, and sometimes they emit two photons which are in entangled state. I don't want to go into the details of these experiments through which you can experimentally produce these entangled photons. Okay, now let's come to the main point. the EPR argument. Okay, remember I told you that there are two interpretations of quantum mechanics, hidden variable interpretation and Copenhagen interpretation. And Einstein in 1935, 35 or 34, came up with a thought experiment to which he and his colleagues argue that Copenhagen interpretation is wrong. Hidden variable interpretation is correct. So what was the argument? The EPR argument. The argument based on this assumption that suppose that you have two entangled photons, and these entangled photons are suppose are in this state in which the correlation is opposite, so which means that the photon A is horizontally polarized, the B will be vertically polarized, and if A is vertically polarized, then the B will be horizontally polarized. That's the entangled state. And suppose that there are two observers, Alice and Bob, and their observation is subjecting to a rule which is called Einstein principle of locality. So let us first see that what is Einstein principle of locality. If two systems A and B are separated space-like, when you say that they are separated space-like, then not even the light can bring any information from one system to the other system. To bring the information from one system to the other system, you have to move with the speed greater than speed of light. So if two systems A and B are separated space-like, then any action performed on system A must not have any effect on system B because they are separated space-like. No information can travel with the speed greater than the speed of light. So therefore, anything which happens over this system that cannot affect this one. So the result of observation of the Alice in this case, if their measurements are separated space-like, must not affect the measurement of Bob. Okay, but the state is actually saying us something opposite. That if it is horizontally polarized, then it's vertically polarized, and if it's vertically polarized, then it must be horizontally polarized. Now, since in the Copenhagen interpretation we assume that the polarizations of these photons are not defined before the act of observation, okay, so that means that it is only the act of observation through which it becomes horizontally or vertically polarized. So if the Alice find that this photon is horizontally polarized and that is happening through the act of observation, and since we know that this will be vertically polarized, then this information must pass to the Bob that, okay, I have become horizontally polarized photon, so you must be vertically polarized. This is the requirement of our state, okay? So some information has to travel from A to B, okay? Now from this you probably will be thinking that perhaps Einstein was trying to prove that since no information can pass with a speed greater than velocity of light, so entangled state cannot exist. That was not his argument. His argument was the following. So since no information can travel with a speed greater than the speed of light, Einstein know that. In fact, this principle itself was developed by him. Okay, no information can travel with a speed greater than speed of light. So therefore, this correlation implies that their polarization were defined before the act of observation. Okay, before the act of observation, it was defined that this photon is horizontally polarized and this is vertically polarized. Or the other possibility, before the act of observation, it is defined that if it is vertically polarized, it's a horizontally polarized. So that means that when these photons are created, their polarization were defined at the time of their creation, not after the act of observation. Okay? Now if their polarizations are defined at the time of the creation, then there must be certain variables which will be fixing these polarizations. These variables are called hidden variables. So let me explain it with a simple example. Where are the boxes? A small, simple demonstration. So what Einstein was trying to say, suppose that I'm a one who prepare these entangled photons, not entangled photon really. I have two gloves. One is the right-handed glove and the other is left-handed gloves. fold them so that I don't know that which one is right-handed and which one is left-handed. Okay? So I just shuffle them. So even you also don't know that which one is right-handed and which one is left-handed. I put them in the box. Okay? So one box, which is the Alice box, that is sent to the Alice, and the other is sent to the Bob. Okay? Now the Bob open it, and the Bob find that it's a right-handed box, right-handed glove, and he immediately know that it must be the left-handed. No, obviously in this case, no information has passed, and no, there's no requirement of passing any information, because at the time of creation, it was fixed that which one is right-handed and which one is the left-handed. So that's how the Einstein argued that the Copenhagen interpretation is incorrect. There are certain hidden variables which fix the outcome of your, which fix the values of the physical observable. They are not fixed by the act of observation. Okay? So that was the EPR argument. So let me show some details. So Alice measured the polarization of this photon, and for this she has a polarized beam splitter. So polarized beam splitter is an optical instrument. If the photon is horizontally polarized, the beam splitter allows it to move in the forward direction. So there is a detector. So if this detector detects a photon, then Alice knows that it's horizontally polarized. And if the photon is vertically polarized, then the polarized beam splitter reflects it at the 90 angle, where we have a detector. So if a photon is detected at this point, then the Alice knows it's vertically polarized. So Alice has assigned two quantities, a physical observable A, which is taken +1 if it is detected here, and it is taken -1 if it is detected here. So if the photon is horizontally polarized, for Alice A is 1, and if it is vertically polarized, for Alice A is -1. Similarly, same operators is also used by the Bob with two detectors. His observable is called B. So B is +1 if it is horizontally polarized, and it's -1 if it's vertically polarized. So what happened in this case? So whenever the Alice find that the photon is horizontally polarized, then the Bob find that it's vertically polarized. So whenever A is +1, the B is -1, right? And whenever the Alice find that it's vertically polarized, the Bob find that it's horizontally polarized. That means whenever A is -1, B is +1. So there's a perfect correlation between the observation of the Alice and Bob. So that means that if they do ensemble measurement, do this experiment again and again, and whenever A will be +1, the B will be -1. Whenever A will be -1, the B will be +1. So therefore, the product, the average of the product of A and B, that will always be -1. Okay. So this is the EPR argument. The locality condition implies that the polarization of the photons were set much before any observation by Alice and Bob. So outcome of the measurements were predetermined. They are predetermined by certain hidden variables, and hence quantum mechanical description of reality is incomplete. So that was the EPR argument. So basically, what they did, they used the principle of locality to argue that the polarizations of these photons are defined before the act of observation. So we don't have to pass any physical information to explain the observed correlation between the Alice and Bob. Okay? So after that, for a long time, there was no study, perhaps because everyone was seeing that the quantum mechanics is working perfectly, so you don't have to bother that whether the hidden variable interpretation is correct or Copenhagen interpretation is correct. And in fact, no one thought of any experiment through which we could decide that whether the hidden variable interpretation is correct or Copenhagen interpretation is correct, unless 1964. So by the way, this is another state. If the photons are in this entangled state, No, in this case, the correlation is not opposite. So if L is find, yeah, if L is find that A is 1, in horizontally polarized, then the Bob will find that it is also horizontally polarized and B is 1. And if the L is find that A is minus 1, then the Bob must find that the B is minus 1. So if the photons are in this entangled state, then they will be perfect correlation. I mean, in this case, they will be perfectly anti-correlated. That's an appropriate word. And in this case, they will be perfectly correlated. So the average value of AB in this case will be plus 1. Okay, so unless until 1964, so there was a huge period in 35 when EPR paper came, and 1964. So in 1964, John Stuart Bell devised a method through which it is possible to test experimentally that whether the hidden variable interpretation is correct or the Copenhagen interpretation is correct. So he actually did not perform the experiment, he just gave a way, introduced a way through which we can rule out the hidden variable interpretation. Okay? So what was his idea? Basically the idea was that they if you Alice and Bob make measurements on the entangled photon, then there will be certain relations between the correlations of these observables, which cannot be explained by hidden variable interpretation. So that's actually the basic idea. But let me explain it. So we have a same arrangement here. We have entangled photon, and then we have an Alice and the Bob. Alice and Bob are measuring the polarization of these photons through polarized beam splitter along with detectors. Okay? And we are assuming that the photon is in this state, in which the observations of Alice and Bob are perfectly correlated. So if Alice finds that it's horizontally polarized, the Bob will find that it is also horizontally polarized. So that means if Alice finds that A is 1, the Bob will find that B is also 1. If Alice finds that the A is minus 1, the Bob will find B is also minus 1. So the observation are perfectly correlated. So what was the Bell's idea? So he suggested that suppose that Alice and Bob measure the polarization of the photon with respect to the axes which are rotated at a certain angle. So previously we were supposing that the polarizations are measured with respect to these axes. If this is axis of horizontally polarized photon and this is axis of vertically polarized. Now here the Bob suggested that let the Alice measure the polarization with respect to axes which are rotated at a certain angle. Let this angle is alpha. Okay? So the Alice will be measuring the polarization with respect to these perpendicular axes which are rotated at angle alpha with respect to the standard axis. Now similarly the Bob will also measure the polarization with respect to the rotated axis, and its axes are rotated at angle beta with respect to the standard axis. Now how the Alice and Bob can measure the polarization with respect to the rotated axis? There are two ways. Either they can change the alignment of their polarized beam splitters. Okay, they just rotate the axis to a certain angle, and similarly the Bob will also do this same thing. But since they have to do this again and again at different angles, so that will be not experimentally feasible. So the experimentally feasible way will be to use a Faraday rotator. Now the Faraday rotator is a cylinder along which we have applied a strong magnetic field. And when electromagnetic wave entered in it, then its polarization is rotated at a certain angle. And the angle at which the polarization will be rotated, that is directly proportional to the magnetic field. So both Alice and Bob, they have a Faraday rotator, and they applied just a current through the coil through which this magnetic field is produced, and by changing the value of the current, they can change the magnetic field, and by changing the magnetic field, they can change the angle at which their axis will be rotated. So that's the far more feasible. Okay, so now in this case, what will be the value of AB average? Right. Now, if they do the measurement with respect to rotated axis, in this case, we see that there will be no perfect correlation, right? So, what will be the A? So, what will do? The Alice will do the observation, and she will collect the data. And whenever she will be measuring a photon, she will either measure that A is +1 or -1. And similarly, the Bob will also be performing the experiment on his side, and he will be collecting the data of the values of P, which will be either +1 or -1, and then they will share their data. So what they will do, that they will take the product of their values and then take the average, which can actually also be written in this way. So what we can do, that what's the probability that the product is -1? You can calculate the probability from the sample easily. So you have to see that in how many events the product of A, B was -1. Divide it with the size of the ensemble, that will give you the probability of -1. Multiply it with the -1, and then what is the probability that the product is +1? Multiply it with the +1, so that will give us the average value of A. We call it a correlation. So since in this case they will not always agree or they will not always disagree because of these rotations, so this AB average will not be +1. Okay, it will be something different. So what it will be, if you calculate this correlation, if you want to calculate this correlation using quantum mechanics, then you have to calculate the expectation value of this operator. This is the rotation operator, which is equal to this one, and you can easily calculate this expectation value. And it's just the direct product of this matrix with itself, but with two different angles, and that will be basically 4x4 matrix. This is also 4-dimensional state, and you can easily calculate this matrix element. We find that this correlation is cos 2 alpha minus beta. Okay, so that tell me that what would happen if they rotate at a different angle. Suppose that they're not rotating, or they are rotating at the same angle. So that means alpha, beta are 0, or they are same. Either way, the difference is 0. You have cos 0, the cos 0 means +1. So when the average value of AB is +1, so that means their observations are perfectly correlated, as is indicated by this state. But if, for example, the difference of this angle, alpha and beta, is say 45 degree, then it will be cos 90 degree, which is 0. The 0 means there will be no correlation. Sometimes the answer will be +1, sometimes the answer will be -1, the answer of this product. So it will be +1, as many as time it will be -1, so average will be 0. So there will be no correlation. And if alpha minus beta is 90 degree, then this will be cos 180, and so that you will have -1. So in this case, AB average is -1, so that means that AB are perfectly anti-correlated. So their observation will be correlated, no correlation, or perfectly anti-correlated. That just depends on the choice of the angle of rotation. If alpha and beta are same, then perfect correlation, and if the difference is 45 degrees, then there is no correlation. If the difference is 90 degrees, then there is a perfect anti-correlation. So the correlation means the average value of AB depend on the angle of these rotation. That's the first thing. No, we can derive a mathematical result, which is called Bell inequality. And in fact, I will go to the mathematical details of this derivation because they're very simple and you can easily understand. No, the Alice and Bob are required to do the measurement at two different angles. Alice is required to choose either of these two angles, angle of rotation, alpha or gamma. And similarly, Bob is also required to choose either of two angles of rotation, beta or gamma. It should be noted that the second angle that is taken same, but the first angle is different. And correspondingly, we have two different observables for the Alice. A, when she choose angle alpha, and CA when she choose angle gamma. And similarly for Bob, you have two observables. B when he choose angle beta, and CB when he choose angle gamma. Obviously, A is +1 or -1 depending upon it's horizontally or vertically polarized or detected by this detector or this detector. Similarly, CA, B and CD are also +1 or -1. So one thing we can tell that CA and CB, they will always be same. Why? Because for CA and CB, the angle is same, and when the angle is same, then the cos 0, which means perfect correlation. So that means if it is +1, it must be +1. If it is -1, it will be -1, right? So this is the experiment which we perform. Alice and Bob are required to choose between two axes of rotation, alpha, gamma, and similarly Bob is also required to choose between two axes of rotation. And no, we cannot define three correlations. The correlation AB means the average value of the product of A and B. What is A? Remember, A is the result of measurement when angle is alpha, and B is the result of measurement of the Bob when the angle is beta. So from the data which they have collected, we can calculate this correlation. And then the second correlation is AC, means the choice of Alice is alpha, and the choice of Bob is gamma. The third correlation is CB, so that means the choice of the Alice is gamma, and the choice of Bob is beta. And the fourth possible correlation is CC, means both choose the gamma. Now in this case, we already know that the answer will be +1. So from the data of the measurement of Alice and Bob, we can calculate